Beautiful. It's an interesting word, but have you ever stopped to really think about it? What does it really mean? What is beauty? What defines it? Is there some sort of mathematical constant or something? And it turns out that that's called the golden ratio. So let's explore it a little more. What is it? Well, suppose I draw a line, and then I decide that I'm going to break that line in two. And I'm not just going to break it anywhere, but in a very, very special spot. And then I start giving them labels, and I make the shorter one B and the longer one A. And the only way that this line could ever be the golden ratio is if A divided by B would equal A plus B divided by A, which means the longer side divided by the shorter side would always, always, always have to equal the total of the sides divided by the longer side. And it turns out this does happen in a very particular case, but we've got to figure out exactly what number it happens for. Now it turns out this number has a special name, and that name is phi, the lowercase phi to be exact, and phi is the golden ratio. It's a constant, just as pi is 3.14159, and so now we can begin rearranging the equation, and so a plus b over a is exactly the same thing as a over a plus b over a, and so that makes it simpler, and then it turns out that a over b is the exact same thing as phi, it's what we just defined it. And then, of course, there's the whole thing about how a over a is exactly the same thing as 1, and then b over a is actually the inverse of a over b, therefore it's the inverse of phi, so 1 over phi. And let's get that phi out of the denominator, so let's just multiply both sides by phi. So on the left side, phi times phi is of course phi squared, and over there phi times 1 is phi, and 1 over phi times phi is just 1. And we really ought to just pause for a second and look at that and see that phi plus 1 equals its square, which is pretty cool for a constant. But anyway, let's go ahead and solve it, and we're going to have to convert it to a quadratic, so let's move everything over there, and that looks good. And so now we're just going to have to use the quadratic formula, so let's go ahead and do that. And assuming that these new variables, a, b, and c, equal the coefficients 1, -1, and -1, then negative b plus or minus square root of b squared minus 4ac all over 2a. And I highly encourage you to do that calculation yourself, but just in case you don't want to, here's the answer, which happens to have an actual evaluation, so are you ready? Here's phi! Here it comes, and it looks like the value is 1.61803398887, and this is a really important value because this is phi. But up until this point, you probably are going to say, who cares? So let me tell you why you should care. Now that we have the value of phi, we're actually able to figure out what numbers could actually make a golden ratio by seeing what two numbers would divide to equal phi. So let's get started. It looks like 34 and 55 work. That's a little interesting. It looks like actually 55 and 89 work. Also 89 and 144. And let's stop and look at this because there's a pattern forming. Because I see 55 as A in one spot and B in another, and I see the same thing happening to 89 and the same thing happening to 144. So let's go analyze some things, and I guess we could just list these out one by one, 34, 55, 89, 144, and what is the pattern here? And actually it looks like 89 might be the result of 55 plus 34. Well, that's interesting. I wonder if 144 is the result of 89 plus 55. Oh, it is. So maybe we could just keep doing this. 233 is 144 plus 89, and 377 is 233 plus 144. And what the heck, let's just start this from 0. 0, 1, 1, 2, 3, 5, 8, 13, 21, and then 34, of course, and that's a lot of numbers. But actually it's not, because these are numbers between 0 and 377 that will actually work for the golden ratio. And that's pretty cool, but you have to understand that if you take 1 divided by 1, you will not get phi, and if you take 2 divided by 1, you will not get phi, and if you take 3 divided by 2, you'll get closer, but still no cigar, and the point I'm trying to make is that the further you go, the closer your number will be to phi. And of course these ideas are not my own, I'm simply explaining theories already proclaimed. For example, Euclid gave the formal definition of the golden ratio, which he called the extreme and mean ratio. And way before that, the Greeks were using the golden ratio in their architecture before it ever was a thing. And then of course there's the Fibonacci sequence made by Fibonacci himself, although he did not start from 0 in the Fibonacci sequence, by the way. And of course, one of my personal favorites is Johannes Kepler, who proved that the further you go in the Fibonacci sequence, the closer you are going to approach phi, the golden ratio, when you divide a number by its immediate predecessor. And I really want to emphasize these topics because they're hardly ever taught in high school, and they're sometimes taught in college, and it's not because they're so difficult to understand, but simply because they're not seen as important enough. And they really should be, because they're everywhere in nature. For example, the golden rectangle can be constructed by values of the Fibonacci sequence and actually construct a spiral that is present in pine cones and leaves and countless other things in nature. And we can actually use phi as a fraction and actually figure out how petals are arranged on a leaf or a flower so that no one petal is over top of the other and therefore blocking the sunlight. And the list goes on and on and on. So I guess what I would encourage you to do is to just step back and look into nature and understand the consistency of mathematics within nature, and just think about how interesting it is that everything around you follows basic principles of mathematics.